Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is actually the final video in a series on graphing polar curves. Up to this point, I really haven't talked too much about symmetry, mainly because I wanted you to really get an idea of how to graph a curve, spend time graphing curves, that type of thing. But there is a way to speed up the graphing process, and that is by using symmetry. Now, before we can delve into these theorems that are going to follow, there are two major issues we need to discuss. Let's first investigate the role of the sine of A in the graph of r of theta is equal to a plus or minus b sine of theta. So here we are in Desmos right now, and actually let me put this in polar mode. So I just go over here and I'll put this in projector. And actually I don't need the grid anyway. Well, that gives me the polar axis, so I guess that's kind of nice. And what I did is I just typed in r is equal to a plus b sine of theta. It is automatically assumed whenever you say r is equal to some function of theta that it's polar. And then notice that it automatically asks me if I want to add a slider for these parameters A and B, and I'll just say yes, I want a slider for all of them. And I should also increase the angles with which theta will go through. 0 to 2 pi is fine. Let me zoom in there. And I'll go ahead and adjust A here, and I'll adjust B. Let's get some interesting curves here. So here we have that B is greater than A. So we have a limison with an inner loop. Now, the investigation we're going to do is about the effect of the sign of A, the SIGN sign. So if I were to go to A up here and put a minus in front of it, notice the graph did not change. And just to let you know, that should automatically, if there's an effect, that should automatically affect the graph. For example, if I put a 2 here, it automatically affects the graph. But for some reason, a negative doesn't. And if I adjust A to be, let's say, larger than B, and then I go and I put a negative in front of A, notice it still does not adjust the graph. What if instead I went for negative values of B? In other words, I shift this to the negative y-axis. Again, let me put a minus sign in front of A, nothing happens. What if I let A equal B? So here they are, we have a cardioid, and here I'll go in and just say negative A, and again, nothing happens. Well, what if I instead say I'm dealing with the cosine? I could take off that negative and nothing would happen. The point here is that the sine, SIGN, sine of A, plays no role in actually the graph other than when you start plotting points. For example, I've adjusted everything slightly and I've included the point XY on here. X is R cos, Y is R sine. And if you look at the graph over here, I adjust that and it showcases the path of travel, right? So that's how the curve got carved out. If instead I put a negative A here, notice that point moved. But when I carve out the path, it still carves out an entire circuit from 0 to 2 pi. So the point is the sine, SIGN, sine of A, just moves the initial point of drawing. That's all. It just adjusts where we start drawing. But if we're willing to draw from 0 to 2 pi, we'll get the same picture no matter what. That is only true, by the way, when you have A plus or minus B sine of theta or cosine of theta. So that's the first thing I wanted to talk about, was that the value of A, as far as the plus or minus sign, will not affect the graph at all. And that's what I wrote here. The graphs of r equals a plus or minus b sine of theta and r equals a plus or minus b cosine of theta are completely unaffected by the sign of a, as long as you're graphing a full circuit. That's the caveat there. The second issue we need to discuss is really about understanding theorems in general. The theorems that are associated with the symmetry of polar curves often get misconstrued. So let's talk about failing the antecedent of a theorem. You might say, what the heck is an antecedent? Well, theorems generally have two parts, really. They have what we call the if part and the then part. Like, if it's raining, which it is right now actually, then it must be cloudy. That's a theorem. If it's raining, then it must be cloudy. The if part is called the antecedent. The then part is called the consequent. So the question is, what if the antecedent isn't actually true? What if somebody says, if it's raining, then it must be cloudy, and you walk outside and it's not raining? Does it mean it's not cloudy? No. If the antecedent is not true, you can't even begin to talk about the then part. So don't worry about the then part. The point is, if the antecedent, the if statement, is false, it does not immediately mean that the consequent is false. There are some hefty theorems in mathematics where it is the case that if the antecedent is false, then the consequent must be false. However, most theorems are not like that. For the most part, this little oddity is not a huge concern in mathematics, not for those who are at the lower division level, because you don't really run into any caveats to theorems, except now. The theorems that I'm about to present, if the antecedent for these theorems is false, for any of these theorems is false, it does not mean the consequence is false. And so I just need to state that. You'll see, and I'll try to draw your attention to it as we move forward, what I mean. So the first theorem is about the symmetry about the line theta is equal to pi over 2. When we're dealing with the polar coordinate system, theta equals pi over 2 is the vertical line that would normally represent the y-axis. So we're really talking about what we would often call in Cartesian systems an even function, a function that is symmetric about the y-axis. In this case, it's not the y-axis, so we just call it the line, theta equals pi over 2. The same result, basically. So here's the theorem. If, that's the antecedent part, if the given polar equation remains unchanged when r and theta is replaced with negative r and negative theta, that's the entire antecedent, then the graph of r is symmetric about that line. So this is, the rest of that, by the way, is, the rest of the sentence is just repeating what I said earlier about those equations of the form a plus or minus b sine of theta, or a plus or minus b cosine of theta. You don't need to take into account the sine of a. Okay, so that's kind of important. The sine of a actually does not play a role in whether or not the graph changes the look. So that's just something we'll delve into. However, going back to our discussion about the theorem breaking or not, let's suppose that I give you a polar equation and you substitute in negative r and negative theta, and for some weird reason, that equation does not turn back into its normal self, right? So if I substitute that in and it doesn't, and it changes, it could still be the case that the graph is symmetric about the line theta equals pi over 2. So this says nothing about if the if part fails. It says nothing about that. All it says is if the if part is true, then we can guarantee it's symmetric about pi over 2. So let's go ahead and use some symmetry to graph this function. The goal here is to replace theta and r with negative theta and negative r to test symmetry. So replace, I'll even say that here. We'll replace r and theta with negative r and negative theta. Now, as written, if I didn't mention something earlier, you would say, okay, so negative r, let's see, is that equal to, or is this the same? Basically, maybe I should just say negative r is equal to 2 minus 6 times the sine of negative theta. So notice what I did here. I replaced r with negative r, and I replaced theta with a negative theta from this equation. Okay. Now what we're going to do is a little bit of manipulation. We know that sine is an odd function, so this implies that negative r is 2 plus 6 sine of theta, and that is because sine is odd. I'm just going to justify it this way. And then let's go ahead and multiply everything by -1 because I want to get r equals. I want to see if it turns back into the original equation. So you multiply everything by -1 and you get the following. R is equal to a -2 minus 6 sine of theta. And notice this equation is not actually identical to the original equation. These are not the same. In fact, I'll use 2 different highlighters for that because they're not the same functions. It's very close, don't get me wrong. R in the yellow highlighting, or I've noticed in my YouTube videos it looks green, but it's supposed to be yellow. R in the yellow highlighting is 2 minus 6 sine of theta. However, when we replaced r with negative r and theta with a negative theta, we end up with r equals a -2 minus 6 sine of theta. So obviously, the equation did not remain unchanged, which according to the theorem we just took a look at, will say nothing. If the given polar equation remains unchanged when r comma theta is replaced with negative r comma theta, well, unfortunately, it did change. So we can't even read the rest of that theorem. It says nothing. However, my little caveat in this theorem is this piece right here, and this only holds for the equations that we're dealing with in that example. If the given polar function is of the form r is equal to a plus or minus b times a cosine or a sine, then you don't have to worry about the sine of a. Okay? So not worrying about the sine of a, I'm just going to say the equation did change, but the change was only with the sine of a. The change was only with the sine of a. And that just means that that equation right there, remember, the graph of r is equal to a plus or minus b sine of theta is the same graph as r equals negative a plus or minus b sine of theta. So we could just say this equation is the same as r is equal to the opposite of that -2, which is 2, minus 6 sine of theta. Just because of that one single caveat. Well, now I could say, because when we plugged in negative r and negative theta, we arrived at an equivalent equation, that means this function must be symmetric about the line theta equals pi over 2. Thus, I'll actually write it right here. R is symmetric about theta equals pi over 2, which basically means I only need to graph half of it, and then I can copy the graph over. So let's go ahead and start to graph the original function, which was r is equal to 2 minus 6 sine of theta. And I will start the way that I've been teaching it, which is graph y is equal to -6 sine of x plus 2. And I'll just quickly jot out that. In fact, I'll do it live rather than pausing or anything like that. So I have y is equal to 2. It's a negative sine function, so it looks like that. Its amplitude is 6, so it goes from 2 up to add 6, 8, and 2 down to subtract 6, -4. So somewhere in between, probably right about maybe here, is the x-axis. So I just chicken scratch that out. That's okay. That's 2 pi right there. That's pi. Here's pi over 2. And here's 3 pi over 2. Real quick graph, nothing fancy. And then I'm going to use that graph to help me actually graph the true polar equation. So I graph the pole and the polar axis right there, and then I just go over to my graph. And remember, it actually started high, just a sloppy graph here. That's where my graph actually starts. So when x is equal to 0, in other words, my angle is 0, I'm throwing stones directly in front of me. Okay. So how far in front? 2 units in front. So I'll go ahead and graph that out. I have a ruler down here, and I'll just be somewhat accurate about this. So 2 units in front will be, let's just say here. Okay. So that's 2 units in front. And then before I even rotate to look at pi over 2, well, I suppose you could say, well, we continue going and we rotate until we get to pi over 2. But by the time you're facing pi over 2, you're throwing stones negative or 4 units behind you. So that by the time you're facing this direction, you're throwing stones 4 units behind you. So I'm just going to quickly tilt that, and 4 units below, 1, 2, 3, 4 units below right there, I have stones behind me. The question is, what does it look like in between, right? So I don't know. Let's find out. Let's see. So from 0 to this point, right here, I was throwing stones in front of me. So it was something like this. And then as I continue to turn, I start throwing stones behind me. So I might have been facing this direction when I dropped the stone at the ground. Now as I continue to rotate around, right, I continue to throw stones behind me. Now I'm not quite done. I'm almost done, honestly. But let's continue forward. Now suppose that you start looking beyond the angle of pi over 2. So you continue to throw stones beyond or behind you as you turn to the right or to the left of pi over 2. So you continue to throw stones behind you, but at some point you're going to throw a stone at your feet. So that's something like this. Well, I could have told you that it did that because it's symmetric about the pole. Once I got this part done, I could have easily just said, oh, and then this. Oh, and then this, by the way, because it's symmetric about the pole. And then let's see, once we get to the pole, we start throwing stones in front of us until we get to pi, which is exactly what I just drew. It's all this right here. Then I continue rotating past pi, and I'm throwing stones in front of me until they get to the maximum distance of 8 at 3 pi over 2. So facing an angle of 3 pi over 2, I'll throw stones 8 in front of me. That's 1, 2, 3, 4, 5, 6, 7, 8. So right about here. It's supposed to be blue. So it does something like this. But because it's symmetric about the line, the vertical line, let me draw it in here. Because it's symmetric about this line right here, I could just copy the rest of the graph over. That's basically how you would use symmetry. I know it's symmetric about that line pi over 2. This case specifically was almost a useless case of being symmetric about the line pi over 2, mainly because we already had graphed parts of it. Right? Once I graphed this part, I could have easily said, oh, it's symmetric, so let me graph this other part. And when I graphed this part, I could have said, oh, it's symmetric, so here's the other part. And then graphing this part gives us the symmetry for this part. So that is a guide to graphing using that type of symmetry. Once you get used to it, it's not bad at all. Now, the next theorem is about symmetry about the polar axis, which is what we would normally think of as symmetry about the x-axis. If the given polar equation remains unchanged when r comma theta is replaced with r comma negative theta, then the graph of r is symmetric about the polar axis. Now again, if you have a polar equation that does not satisfy this initial if statement, then it still could be symmetric about the polar axis. You just don't know, but it could be. So it's kind of a weird situation. So let's see. Now we have two ways to test symmetry. Our two ways are this. If negative r comma negative theta, plugging that in, leads the same function. That's supposed to be function, but for some reason it just got screwy on me. The whole screen did. Same function. Then we have symmetric about, about theta equals pi over 2. And in this case right here, if r comma negative theta becomes the same function, then we have symmetric about the polar axis, which is basically symmetry about the x-axis. So let's go ahead and use symmetry to graph this function right here. First thing I'm going to do is just test it. Plug in, I'm going to let theta become negative theta and see what happens. So r equals cosine of negative 2 theta. Well, cosine is an even function. So that is going to be cosine of 2 theta, which is the original statement. So this implies unchanged. Nothing changed when we plugged in a negative theta, which implies we definitely can use that theorem. It's symmetric about the polar axis. Symmetric. So we only have to graph half of it about polar axis. And you can also, by the way, test the whether or not it's symmetric about the line theta equals pi over 2. It's not going to be, but I'll just showcase it. So if you tried the other symmetry, so if you let r theta become negative r comma negative theta, you would have negative r is equal to cosine of negative 2 theta. Cosine is even, so that's cosine of positive 2 theta. And then you would multiply both sides by a negative because you want to get r is equal to. But you would get r is equal to negative cosine of 2 theta, which is not equal to cosine of 2 theta. So it is not symmetric. Well, we can't say it's not symmetric about the line theta equals pi over 2. We just can't apply that theorem. So this says nothing. It's just that we can't apply that theorem. We can't assume it's symmetric about the line theta equals pi over 2. But we definitely can assume it's symmetric about the polar axis. So let's go ahead and quickly graph the y equals the cosine of 2x. I'm going to write that over here. Y equals the cosine of 2x. That's just a regular old cosine curve, but it goes through 2 of its cycles in what normally would be a single cycle time. Right? So I'm just throwing in all the important points here. Pi over 4 is right there. Hopefully we don't need more than that. And now I'll graph in here the pole and the polar axis. So the pole I'll just put right there, and the polar axis I'll do this. Now, if you recall, this is one of those situations when you have a multiple angle like this. These are usually pretty terrible to graph, honestly. They're just terrible to graph. They're not fun to graph by hand at all. However, this one might be okay. Let's find out. When your angle start at 0, you're throwing a rock, by the way, this is 1 and negative 1. You're throwing a rock 1 unit away. So I will pretend as though, just to get something going, that's 1 unit away from the pole when you're facing an angle of 0. By the time you face an angle of pi over 4, the rock, you're dropping rocks at your feet. So it looks something like this. Okay, you don't have to make that sound though. By the way, because it's symmetric about the polar axis, I know it also looks like that. Okay. Then as I move beyond pi over 4, I'm starting to throw rocks behind me. Again, throwing rocks this way because I'm facing that way. And so let's see what happens here. I throw rocks behind me until I face pi over 2. When I face pi over 2, which is this way, those rocks are 1 unit behind me. let's go ahead and at least plot that point. And just from the path of travel, I know it's going to look like this. However, because this function is symmetric about the polar axis, I know it's going to look identical up above. It's like a mirror image up above. Then I continue and I say, okay, well, as I move past pi over 2, I'm still throwing rocks behind me. So again, I'm moving past this pi over 2 angle, and now I'm looking this way, all the way until I get to, by the way, 3 pi over 4. So I continue throwing rocks behind me, until I get to 3 pi over 4, where the rocks will land at my feet. Again, I continue throwing behind me, until they land at my feet. Well, because this is symmetric about the polar axis, I know it's going to look like that up there as well. And now that I'm facing 3 pi over 4, I start throwing rocks in front of me until I face pi, when they are 1 unit in front of me at that point. So I start turning and they kind of bow out and do this type of thing. But again, because it's symmetric about the polar axis, it's got that. And I'm completely done with my graph. So this is a good way to graph when you have very complex polar graphs like this, is to use these theorems. In fact, I'm going to start really kind of writing them down nicely so that we have them for each of our examples. So there we go. It's nice and clean right there. If we replace r comma theta with negative r comma negative theta, and after some manipulation, the equation looks unchanged, it must be symmetric about theta equals pi over 2. If, on the other hand, we replace r comma theta with r negative theta, and after manipulation, the equation is unchanged, it must be symmetric about the polar axis. So let's see how far we can carry that argument. The final type of symmetry we often see is symmetry about the pole. If a polar equation remains unchanged when r comma theta is replaced with negative r comma theta, then the graph is symmetric about the pole. This is stuff that looks like the following. You might end up giving, this is called a lemniscate. Lemniscates look like this. Well, okay, they look better than that, honestly, but it's supposed to be the same picture on both sides of that. So they're supposed to be the same, but I couldn't. I'm a terrible artist. Anyway, if you can rotate it 180 degrees and it's the same picture, it's symmetric about the pole. So this really does kind of build all of our symmetries into one final statement, which is all the stuff we said just a moment ago, and then the third paragraph down there, if we replace r comma theta with negative r comma theta, and after some manipulation the equation is unchanged, it must be symmetric about the pole. Now, polar curves can have multiple symmetries. So if you find that you have a bunch of all 3 symmetries or something like that, then there's very little graphing that you need to do, and you should be super happy about that. For example, this guy is like a dreaded polar curve to graph. We don't like graphing this because this is a 4-leafed rose. And if you didn't know that, you'd be stuck graphing the whole stupid graph, doing the whole stupid graph. But we can go through and plot out, or not plot out, but we go through and look at these conditions right here and see if we have any symmetries. So let's go ahead and do that. And I just wanted to move that off to the side because it was annoying me. So let's see, let's start with symmetry about the line theta equals pi over 2. Let's take r comma theta and trade it out for a negative r comma negative theta and see what happens. So let's see, negative r is equal to sine of negative 2 theta. Sine is an odd function. So that tells us that negative r is equal to negative sine of 2 theta. Now I want to solve it for r, so at least I can compare those two equations. Multiplying both sides by a negative, you would get r is equal to sine of 2 theta. And that is awesome, because now we have that our curve is symmetric about that vertical line theta equals pi over 2. Well, let's see if we have any other symmetries. Let's try the symmetry about the polar axis. So we're going to replace theta with a negative theta. So the next one is r comma theta. We're going to trade that out for an r comma negative theta. So let's see, r stays the same, but theta becomes a negative, and sign is odd, so you can move the negative outside, and this is definitely not the original function. So unfortunately, we can't say anything. It could be symmetric about the polar axis, but we really can't guarantee that. So let's try the last one. What if we replace r comma theta with negative r comma theta? If after some manipulation the equation remains unchanged from the original equation, then we know it's symmetric about the pole. So we can rotate things 180 degrees. Let's take a look. I have r comma theta. I'm going to trade that out for a negative r comma theta. Well, let's see, negative r is equal to sine of 2 theta. Well, unfortunately, if you multiply both sides by a negative 1, that would imply you have r is equal to a negative sine of 2 theta, which is not the original function. So again, we cannot guarantee that we have symmetry about the pole. However, this is a very interesting curve in that it has all three symmetries, honestly. It's just that the theorems, the antecedents, weren't satisfied for the last two, but it is actually symmetric in all three aspects. So let's go ahead and just use the green symmetry here to help us graph. It's symmetric about that vertical line pi over 2. So I've just quickly jotted out the sine of the double angle, or sine of 2x there. And I'm going to be kind of sloppy with this, but that's okay. Here's my pole, here's my polar axis. When we face the angle of 0, we have a rock that we drop at our feet, because if you take a look at that, facing the angle 0, the output's 0. But as we turn as we turn to the angle of pi over 4, once we hit the angle pi over 4, the rock is 1 foot in front of us. So we are going to start throwing rocks in front of us until we get to the angle of pi over 4, which will be 1 foot in front of us. So start here, and then as you turn through angles, eventually you have a rock that's 1 foot away, but it takes a little bit to get there, right? Because that distance is increasing as you're turning. Now remember, we're going to use the fact that this curve is symmetric about the line theta equals pi over 2. Theta equals pi over 2 is this vertical line. So I could start copying it, but I'm not yet, because I just want to see how far I can get with the symmetry. As I continue to turn, I keep throwing rocks in front of me, but eventually by the time I'm facing pi over 2, they're at my feet again. So I continue to turn past this angle and I start throwing rocks, but they get closer and closer to me, and by the time I'm facing up, they're at my feet. All right, now I'm going to continue to turn here past pi over 2, and by the time I get to 3 pi over 4, which is this angle right here, I have rocks 1 foot behind me. So again, I'm facing this direction. I have thrown rocks a foot behind me by the time I face that direction. So the curve has done this. And again, as I continue that path, I turn to face pi. By that time, the rocks are back at my feet. And now, because I have symmetry about that line, I could just do this. It's supposed to be beautifully symmetric, but my drawing is terrible. So all I needed was to graph half of that. Notice this is symmetric about the pole, it's symmetric about the polar axis, and it's symmetric about the line theta equals pi over 2. Yet, our tests only showed that it was symmetric about the line theta equals pi over 2. Again, it's a great example that your tests might fail and it still might be symmetric. But the tests that succeed are awesome, because then you only have to graph half of it, and then the rest of the graph you can quickly do. All right, that finishes out this lecture video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.